A single object can rewrite the story of human innovation. Deep in Egypt, archaeologists have unearthed an artifact that defies everything we thought we knew about ancient technology. This is not a statue or a piece of jewelry. It is a complex mechanical device with interlocking parts and precise geometry that seem to belong to a much later era. By the end of this exploration, you will understand the full scope of a discovery that could shatter our historical timeline. We will examine the strange machine itself, walk through the heated debate between experts, and confront the staggering possibility of knowledge lost to time. How much of our ancient past remains hidden in plain sight? The sands of Saqqara hold more than just the echoes of pharaohs. This vast necropolis, a sprawling city of the dead south of Cairo, is where our story truly begins. It was here, in the shadow of the step pyramid of Djoser, one of humanity's oldest stone monuments, that a routine excavation took an extraordinary turn. An international team, a collaboration between Egyptian archaeologists and a European university, was meticulously clearing a lesser-studied sector, a network of tombs belonging to mid-level officials from the late Old Kingdom period. Their work was careful, brushing away millennia of dust and debris, cataloging pottery shards and fragmented inscriptions. Then their tools struck something that did not sound like stone or ceramic. It was a muted, metallic resonance. The object was not found in a royal burial chamber, but within a modest, non-royal tomb shaft sealed for over 4,000 years. Crucially, it was discovered in a clear and undisturbed stratigraphic layer. For archaeologists, the stratigraphy, the sequence of soil and debris layers, is like the pages of a history book. The layer containing this artifact was firmly dated, through pottery styles and carbon dating of organic remains found alongside it, to the 5th dynasty of the Old Kingdom, around 2400 B. See, this date is not a guess, it is the bedrock context of the find. The machine was resting alongside simple grave goods, ceramic jars for offerings and a few alabaster vessels, items typical for the period. This context is what makes the discovery so profoundly disorienting. It was not a later intrusion, not something dropped into an older site. According to every standard archaeological principle, this complex object was placed there when the tomb was sealed, in an era we have long characterized by copper tools and stone craftsmanship. The significance of Saqqara itself cannot be overstated. This was the sacred ground where the art of pyramid building was pioneered, a place of immense architectural innovation. Yet all those innovations were in stonework, in grand, static structures. To find a small, intricate machine here among the tombs of officials shifts the narrative entirely. It suggests the technology, whatever its purpose, may not have been exclusive to the divine pharaoh, but perhaps part of a broader, yet completely forgotten, sphere of knowledge. The mystery was not buried in a lost city or a mythical continent, but right in the heart of one of archaeology's most studied landscapes, waiting in plain sight for its context to be understood. The object that emerged from the dust was utterly perplexing. At first glance, it was a dark, heavy lump, roughly the size of a modern shoebox and coated in a thick, greenish-black patina. Its weight was surprising, far denser than a solid stone carving of that size would suggest. As the conservators began their delicate work, brushing away the crust of ages, the true nature of the find started to reveal itself. This was not a smooth, carved figure of a god or an animal. Instead, the surface was a complex landscape of geometric shapes. There were what appeared to be raised rings, sunken channels, and several protruding stubs of a different, lighter-colored material that looked almost like ceramic or a stone composite. Most strikingly, one face of the object had a series of interlocking, tooth-like projections arranged in a perfect circle. It looked less like a sacred symbol and more like a gear or part of a clutch mechanism. The initial field notes reveal the team's bewilderment. One archaeologist reportedly called it a ritual sensor, while another immediately argued it was a technical component. The debate centered on a fundamental question: was this an object of pure ceremony, designed to symbolize something, or was it a piece of a functional apparatus designed to do something? The deciding factor was the evidence of precise, repeated wear. Under magnification, the tips of those tooth-like projections showed uniform polishing, a smoothness that suggested repeated contact with another surface. Ritual objects are often handled, but they rarely show such specific mechanical abrasion. Furthermore, the channels on its surface were not decorative swirls. They were straight, deep, and met at consistent angles, resembling fluid pathways or alignment guides. This pushed the team toward a monumental decision. They would not catalog it simply as miscellaneous ritual object. For the first time in the context of Old Kingdom Egypt, an artifact was being officially treated as a potential piece of ancient machinery. This shift in perspective was everything. It meant every cleaning step, every scan, every analysis would now be conducted with a new question in mind. Not what does this represent, but how did this work? The artifact was immediately sealed in a sterile container, its journey from the tomb floor to the laboratory beginning under a cloak of intense scientific scrutiny. The first and most critical task was to confirm its age beyond any reasonable doubt. While the undisturbed soil layer provided a strong contextual date, the team employed a multi-pronged approach to build an irrefutable chronological case. They conducted a meticulous stratigraphic analysis, documenting every millimeter of soil and debris above, below, and surrounding the find. This matrix of earth told a clear story of a single, sealed deposition event, with no signs of later digging or disturbance that could have introduced a newer object. To anchor this geology in time, they turned to organic material found in the same exact layer, mere inches from the machine itself. Fragments of reed matting used in the burial rite and residues inside the associated ceramic jars were sampled for radiocarbon dating. This process measures the decay of a radioactive isotope in once living matter, providing a remarkably precise window of time. The results converged on a period between 2400 and 2300 B. C. In Egyptian history, this squarely places the object in the 5th or very early 6th dynasty of the Old Kingdom, the age of pyramid builders, but an age documented solely for its monumental architecture in stone. Concurrently, a non-destructive X-ray fluorescence scan was performed to determine the object's basic material composition. The scan revealed a high copper content consistent with the period's metallurgy, but also showed traces of tin and arsenic, elements used in early alloys, and confirmed the lighter protruding pieces were a finely made faience, a glazed ceramic. This preliminary data created the core puzzle. Every scientific test pointed to the same inescapable conclusion: this was a genuine artifact from the Pyramid Age. Yet its form was a stark anomaly. We have extensive records from this era: tomb paintings, reliefs, inventories of workshops. They show carpenters, stonemasons, goldsmiths, and potters. Not a single depiction or text references a workshop for making intricate multi-component devices with geared elements. The science dated the object, but in doing so, it dated a mystery. The machine was not out of place because it was a fake. It was out of place because our understanding of what was possible in that time appears to be profoundly incomplete. The artifact, now carefully cleaned and stabilized in the laboratory, revealed a sophistication that left the research team in silent awe. Its form was a masterpiece of miniature engineering. The main body, cast from that copper alloy, was not a solid block but a hollow housing. On one face was the most striking feature, a central, raised ring about the width of a coffee mug, and from its edge protruded those 24 identical triangular teeth. They were perfectly spaced, each one showing that same polished flat spot at the tip, a clear sign of repeated meshing with another component now lost. This was undeniably a gear. Radiating out from this central ring were 3 deep, straight channels, cut with a precision that spoke of intent, not artistry. They met at the center like spokes on a wheel, but their purpose seemed functional, perhaps to guide a moving part or to allow the flow of some substance. On the opposite side of the housing, the complexity continued. There was a square socket, its inner surfaces worn smooth, clearly designed to receive a square-ended axial or drive shaft. Next to it, set into the metal, were 3 cylindrical pins of that pale faience ceramic. These were not decorative, they were precisely positioned, acting like alignment dowels or bearings for a plate that would have fitted over them. The entire assemblage brings to mind the interior of a simple wind-up toy or an antique clock before the face is attached, a contained world of calculated movement. Every single part, the gear teeth, the channels, the socket, the alignment pins, spoke of a unified mechanical function. This was not a collection of symbols haphazardly assembled, it was a designed system. The wear patterns tell the final, convincing part of the story. The polishing on the gear teeth is not random scratches, it is a consistent, angled sheen found only on the leading edges, the exact kind of wear produced by turning against another geared surface. The smoothness inside the square socket mirrors this, indicating something rotated within it, again and again. This object did not sit on an altar, it worked. It was part of a larger apparatus, a machine whose purpose has vanished into silence, leaving behind only this intricate, stubborn clue. Faced with this meticulously crafted artifact, a bold hypothesis began to take shape among the more technically minded researchers. They proposed that this was not merely an object, but a component, a surviving piece of a deliberately engineered ancient machine. This is not a casual label. Calling something a machine implies a specific intent, the creation of a device designed to transform or control energy to perform a task. The evidence supporting this idea is found in the object's very architecture. First, there is the matter of precision. The 24 gear teeth are not roughly similar, they are identical in size, shape, and spacing. Achieving this in a copper alloy over 4,000 years ago would have required a template, a consistent manufacturing process far beyond simple freehand carving. This speaks to planned, repeatable production. Second, the object shows clear evidence of assembly. The faience ceramic pins are not glued on, they are set into perfectly sized sockets in the metal housing. The wear inside the square socket indicates it was meant to interface with a separate axial. This is a multi-part construction where different materials with different properties, metal for strength, ceramic for smooth rotation, are combined for a unified purpose. Third, the entire design is governed by symmetry and geometry, not for beauty but for function. The radial channels meet at the exact center of the gear. The pins form a perfect triangle for stable support. The gear teeth are spaced for even engagement. This is the logic of engineering, where imbalance leads to failure. Contrast this with a purely symbolic or decorative object from the same period, like a ceremonial mace or an ornate cosmetic palette. Those items are shaped for meaning and visual impact, their forms flowing and representational. This artifact is shaped for interaction and movement, its forms angular and calculated. The wear patterns are the final, silent testimony. They do not show the random scuffs of handling or ritual rubbing. They show the specific, localized polishing of repeated mechanical action. The hypothesis is compelling because it follows the evidence. The form of this object follows a logic of function, pointing to a level of technical thought we never attributed to the pyramid builders. This discovery, however, did not land in a vacuum of academic agreement. As word of the find spread, a wave of profound skepticism arose from many mainstream Egyptologists. Their counter-argument is not born of closed-mindedness, but of a deep-seated methodological caution. They propose far more conventional explanations, challenging the leap from artifact to machine. The primary and most favored theory within this camp is that the object is an exceptionally elaborate ceremonial item. They point to the rich symbolic language of ancient Egypt, where objects were rarely just functional. Could the gear-like ring represent the sun disk of Ra, its teeth symbolizing rays of light, and the channels depicting the paths of divine power? In this view, the wear patterns might be from ritual handling or from being rubbed against a ceremonial base during religious rites, not from mechanical rotation. Another suggestion is that it was a specialized tool for a mundane purpose we simply no longer recognize, perhaps a unique loom weight, a sophisticated seal press for administrative documents, or a component from a large-scale measuring device. The skeptics forcefully highlight the total absence of parallels. In the entire corpus of Egyptian archaeology, spanning thousands of years and millions of artifacts, nothing remotely like this geared component has ever been found. If this was a known technology, they argue, where is the rest of it? Where are the broken pieces, the workshop debris, the depictions on tomb walls? Their most pointed critique is one of perspective. They warn against the temptation of imposing our modern, machine-oriented mindset onto an ancient culture that thought in different terms. We see gears and immediately think of clocks or engines, but to an Old Kingdom priest, the same shape might have held an entirely spiritual meaning. They urge patience, arguing that labeling it a machine too quickly might actually blind us to its true cultural significance, which could be far more revealing about their worldview than an assumption of lost technology. This skepticism forms a crucial part of the scientific process, a necessary friction that tests the bold new hypothesis against the sturdy bedrock of established knowledge. To resolve this clash of interpretations, science offered a path beyond opinion. The artifact was subjected to a suite of non-destructive, high-tech analyzers, a digital autopsy that peered into its very essence. The first revelation came from advanced spectroscopic scans, which mapped the object's elemental composition with incredible precision. The main body was confirmed as a copper alloy, but not a simple, crude mix. It contained deliberate trace amounts of tin and arsenic. This was significant because adding these elements alters the metal's properties, making it harder, more durable, and better suited for a component meant to endure stress and friction. This wasn't just melted ore, it was a formulated material. Even more intriguing was the purity of the copper base. For its time, it was exceptionally free of the slag and impurities common in contemporary metalwork, suggesting a refined smelting process that few workshops of the era were thought to possess. Next, researchers turned powerful microscopes onto its surface, examining the ghostly fingerprints of its creation. The goal was to answer a simple, profound question: how was this thing made? The tool marks told a story. In the deep, straight channels and on the flat faces of the gear teeth, they found evidence of a repeated, consistent cutting motion. The striations were parallel and uniform, not the irregular, multidirectional scratches left by handheld chisels or files. This pattern is characteristic of a rotary cutting tool, something that turned while the artifact was held steady, or vice versa. The closest modern analogy would be the marks left by a simple lathe or a drill-powered milling bit. This suggested the use of a mechanical aid, a device that could ensure such consistent, linear removal of metal. The concept of a bow-driven lathe using a hardened stone or copper point is not impossible for the period, but no evidence of such tools has ever been definitively linked to Old Kingdom Egypt until now. The microscopic evidence pointed toward a technology for precision shaping that simply does not appear in any known record or artistic depiction. Finally, the wear analysis provided the most compelling argument for function. Specialists in tribology, the study of friction and wear, examined the polished areas. They confirmed that the sheen on the gear teeth was not from random polishing or cleaning. The pattern of microscopic abrasion was directional and concentrated on the leading edges of each tooth, exactly as would occur if this gear had meshed with another and rotated under load for a significant period. The smoothness inside the square socket showed a similar rotational wear pattern. This was the silent testimony of use, This object didn't just sit in a tomb for ceremonial display. It spent part of its life moving, working as part of a larger system. The scientific data began to paint a portrait that challenged conventional history, not of a symbolic trinket, but of a precisely engineered component, made from a purposefully crafted alloy, shaped by tools of surprising sophistication, and worn down by genuine mechanical operation. The mystery was no longer just about what the object was, but about the invisible world of knowledge and workshop practice that must have existed to produce it. To understand just how radical this find is, we must place it beside what we know for certain about ancient Egyptian technology. The people of the Old Kingdom were brilliant engineers, but their genius was channeled in specific, well-documented directions. They mastered the mechanics of massive stone, using ramps, levers, and human power to build the pyramids. For moving water, they employed the shadoof, a simple but effective counterweighted lever for irrigation. The potter's wheel was in use, a beautiful example of rotary motion, but it was a simple, free-spinning device. They understood basic pulley systems for hauling obelisks and likely used a bow drill for creating holes in stone and wood. These were all brilliant applications of fundamental physics, but they represent what we call simple machines: levers, wheels, inclined planes. The artifact from Saqqara represents something entirely different, a compound machine. It is not a single application of force, but an integration of multiple mechanical principles, gears, axles, and likely bearings, all contained within a single housing to perform a more complex task. Think of the difference between using a lone lever to pry up a rock and the interior of a pocket watch, where many tiny levers and wheels interact to track the passage of time. One is a tool, the other is a mechanism. This jump from simple to compound machinery is a monumental leap in technical thought, a leap we had no evidence Egypt made at such an early date. The closest parallel that comes to mind is the famed Antikythera mechanism, discovered in a Greek shipwreck dating to around 100 B.C. That device, an astronomical calculator of staggering complexity with dozens of interlocking bronze gears, rewrote our understanding of Hellenistic science. But the Antikythera mechanism is over 2,000 years younger than the Saqqara object. To find a geared component in Egypt that predates it by more than 2 millennia is not just surprising. It suggests the seeds of complex mechanical thought were planted far earlier, and in a civilization not known for it, only to be lost or forgotten for ages. This artifact doesn't just challenge a timeline, it suggests an entirely separate, hidden branch on the tree of technological innovation, one that grew in silence long before the branches we are familiar with even began to form. The artifact's true nature demanded a perspective beyond archaeology. To understand what this object was designed to do, the research team brought in a different kind of expert: modern engineers and precision machinists. These individuals think in terms of function, stress, and tolerances, not symbolism. Given detailed three-dimensional scans of the find, they were asked a simple, profound question: what does this design enable? Their analysis, grounded in pure mechanics, was revealing. One engineer focused on the central geared ring. With 24 identical teeth, this is a counting gear, she noted. In any geared system, a wheel with this tooth count is ideal for tracking rotations or subdivisions of movement. If this was the drive gear and it meshed with a smaller pinion gear, each full rotation would advance that smaller gear by a precise number of steps. This is the fundamental principle behind any device that measures, counts, or regulates. It could have tracked anything from the passage of time, like a simple water clock's flow, to the number of turns of a wheel for measuring distance. A machinist examining the square socket and alignment pins pointed to the evidence of controlled motion. The square socket means it was driven by, or drove, a shaft that couldn't slip, a design for transferring torque, the energy of rotation. Those 3 ceramic pins aren't just for show, he explained. Their bearings, a flat plate perhaps made of wood or another material that hasn't survived, would have rested on them, held in place but allowed to rotate smoothly with minimal friction. This creates a stable plane for other components to interact with the central gear. The arrangement suggests a contained mechanism where the central gear's rotation was translated into a different kind of movement on this parallel plate. Another specialist looked at the 3 deep, straight channels radiating from the center. These aren't decorative, they're guides, she stated. They could have served to align the device during assembly, or more intriguingly, they could have housed sliding pins or stops that would engage with the gear teeth at specific intervals. This would create a periodic locking or triggering function, like the strike mechanism in a bell or a device that releases something after a set number of rotations. The consensus from this engineering viewpoint was neutral but clear. The artifact's design is optimized for precise, repeatable mechanical interaction. It is a component for a device that required regulated motion, likely involving measurement, counting, or synchronized action. This functional language doesn't prove it was an ancient computer, but it powerfully dismisses the idea that it was merely a symbolic ornament. An ornament doesn't need such precise tolerances, such careful consideration of friction, or such a deliberate arrangement for transferring force. The engineers saw a puzzle of physics, and every piece fit a logic of purposeful work. But what was this precisely engineered component actually meant to do? With its silent gears and worn bearings, the artifact offers no manual, only clues. This has led to a fascinating spectrum of theories, each attempting to decode its original purpose by matching the physical evidence to a plausible historical need. One of the most compelling ideas is that it served as part of an astronomical calculator. The ancient Egyptians were meticulous sky watchers, aligning their pyramids with celestial bodies and developing a calendar critical for predicting the Nile's floods. A device with a counting gear could have tracked lunar phases or the movements of stars. Imagine a simple model where this central gear, turned by hand 1 notch per day, engaged a series of other gears to indicate the changing position of a constellation or the approach of a significant solar event. The wear on the teeth suggests repeated, cyclical use, fitting perfectly with an astronomical tool used by temple priests to maintain the sacred calendar. While not as complex as the later Antikythera mechanism, it could represent that idea's earliest, simplest ancestor. A second, more grounded theory points to practical construction. The precision of the pyramids is legendary, their sides aligned almost perfectly to the cardinal directions. Could this device have been part of a sophisticated surveying instrument? The square drive socket might have held a sighting alidade, a straight edge for aiming, while the geared mechanism allowed for fine, incremental adjustments in angle. The ceramic bearing pins would have provided the smooth rotation needed for accurate measurement across the vast desert plains. This theory connects the object directly to the greatest technological achievement of its era, positioning it not as a mysterious outlier, but as a lost key to the pyramid builder's legendary accuracy. A more ritual-centered proposal envisions it as a temple device for creating awe-inspiring effects. Hidden within a statue of a god, connected by cords to a hidden priest, such a mechanism could have made the statue's arms slowly rise or its head turn, creating a miraculous illusion of divine movement for worshippers. The controlled, repeatable motion indicated by the wear patterns would be essential for a convincing and reliable spectacle. This theory elegantly bridges the mechanical and the spiritual, suggesting the technology served to manifest the god's presence, making the invisible visible through ingenious engineering. Then there are the more speculative ideas that it was a component from a larger, lost machine for tasks like water clock regulation or even primitive metalworking. Yet each theory must be weighed against the artifact itself. The astronomical and surveying ideas strongly align with the evidence of precise, countable rotation. The temple effect theory accounts for the need for smooth, reliable motion. However, the object's small size and apparent lack of a direct interface for an operator, like a handle, suggest it was likely a component hidden within a casing, part of a larger whole we may never fully reconstruct. What remains undeniable is that every serious theory accepts its mechanical nature. Whether it counted stars, measured angles, or animated gods, its purpose was rooted in controlled motion, a silent language of engineering that whispers of a forgotten chapter in humanity's long story of invention. Yet for any device to truly be called a machine, it must have a source of motion. A fundamental question now arises, one that skeptics rightly emphasize: what powered it? The artifact itself offers frustratingly subtle clues. There is no obvious handle, no slot for a winding key, no large hook for a heavy weight. This apparent absence is a major point of contention, often cited to dismiss the entire mechanical hypothesis. How can it be a machine, the argument goes, if we cannot see how it moved? But this challenge invites a closer, more imaginative look at the object's design. The square socket is the most direct clue. A square hole is not for decoration, it is for a square-ended axial. That axial, now lost, was the direct link to an external force. It could have been turned by a simple hand crank, a small wooden lever inserted into a hole on the axial's other end. The wear inside the socket confirms something rotated there repeatedly. Alternatively, the axial could have been part of a larger transmission, receiving motion from another gear or a pulley elsewhere in the apparatus. The three deep channels radiating from the center might also play a role. While they could be alignment guides, they could also have served as anchor points for cords or thin metal bands. Imagine a cord wound around a drum on the central axial with a small weight hanging from its end. As the weight descended, it would turn the gear in a slow, controlled manner, a primitive form of weight drive. Another possibility involves water. If the device was housed within a sealed container, the channels could have directed a slow trickle of water onto a small paddle wheel linked to the axial, using the steady flow from a regulated water clock as its power source. The key realization is that the artifact we have is likely just the heart of the machine, the precision movement regulator. The parts that provided the muscle, the crank, the weight, the water source, were probably made of perishable materials, wood, cord, leather, which decayed to nothing in the tomb's environment over 4 millennia. We are left with a durable, metallic core, the brain of the operation, while the limbs that moved it have vanished. This doesn't invalidate the machine theory, it refines it. It suggests the ancients understood the principle of separating the power source from the precision mechanism, allowing a crude, strong force like a falling weight to be translated into fine, measured motion through their ingenious gearing. The silence of the power source is not proof of its absence, but a testament to the organic materials of the ancient world, and a haunting reminder of how much of their technology may have simply returned to dust, leaving only the most stubborn metallic fragments behind to whisper of their complexity. The silent language of the artifact now demands we listen to the voices of its own culture. If this was a known technology, however specialized, would its echo not appear somewhere in the vast record of Egyptian art and writing? Researchers began a painstaking review, not to find blueprints but to search for hints, for metaphors and descriptions that might take on new meaning when viewed through a mechanical lens. They turned first to the rich iconography within tombs themselves. In several Old Kingdom mastabas, there are curious scenes depicting what Egyptologists have traditionally called ritual objects or divine standards. These are often shown as complex pole-mounted items carried in processions. Their forms a combination of circles, crossbars, and dangling elements. One particular relief from Saqqara shows priests carrying a device that features a prominent central ring with radial spokes, held aloft like a sacred emblem. We have always interpreted these as symbolic representations of cosmic order or divine attributes. But what if, at least in some cases, they were depictions of actual revered instruments? The physical artifact, with its central geared ring and radiating channels, bears an uncanny schematic resemblance to these painted symbols. It is a provocative parallel, suggesting that what we see as abstract iconography might sometimes be a stylized representation of a real, physical object of power and function. The textual search delves into the pyramid texts, the oldest known religious writings in the world, inscribed within the very pyramids of this era. These spells are filled with dense, poetic imagery meant to guide the pharaoh to the afterlife. Within them, researchers have isolated intriguing phrases. The sun god Ra is described as navigating the sky in his bark of millions, a vessel of eternal motion. More pointedly, there are references to the instrument that opens the ways and the wheel of heaven that turns without weariness. Traditionally, these are understood as pure mytho-poetic constructs, metaphors for celestial mechanics. Yet, in the shadow of the geared find, a tantalizing question emerges. Could such phrases also reflect a conceptual understanding of actual mechanisms, a way of describing real, tangible principles of motion and cyclical repetition using the only vocabulary they had, the language of myth and divinity? It is not that the ancients had helicopters, but that their most advanced technology might have been described in the same terms as the gods' machinery, blurring the line between the symbolic and the literal in their records. This leads to the most profound cultural correlation, the concept of Maat. This was the foundational principle of Egyptian civilization, representing truth, balance, cosmic order, and justice. Maat was often depicted as a goddess with a feather, the symbol of perfect, weightless equilibrium. The entire state and religious apparatus existed to maintain Maat, to keep the universe running smoothly like a perfect, silent machine. The newly discovered artifact, with its precise symmetry, its balanced gear teeth, and its evidence of regulated, repeatable motion, is a physical embodiment of this very principle. It is Maat cast in metal, a device that performs order through mechanical harmony. This reinterpretation offers a stunning possibility. Perhaps the most advanced technology of the time was not seen as separate from religion, but as its highest expression, a tool to physically manifest the balanced order of the cosmos. A device for tracking stars would not just be a calculator, it would be a machine for upholding Maat by ensuring the calendar, and thus all rituals and agriculture remained in sync with heaven. A surveying instrument that ensured perfect alignment was literally building Maat into the landscape. This perspective dissolves the modern dichotomy between the spiritual and the technological. For the Egyptians, the most sophisticated mechanism might have been, at its heart, a sacred object, an instrument of eternity that made the divine principle of order tangibly, mechanically present. The artifact, then, may not be an outlier, but a key to understanding a deeper layer of their worldview, one where engineering and divinity were woven from the same thread. This discovery pushes us into a fascinating and contentious category of archaeology, the world of the out-of-place artifact, or OOPArt. The term itself is evocative, describing an object that appears so technologically or historically anomalous within its discovered context that it seems to challenge or even defy the established narrative of human progress. By its very definition, the Saqqara artifact is a textbook OOPArt. It is a complex geared mechanism, displaying engineering principles we associate with a much later era, found in a sealed tomb layer dated to the Pyramid Age. It is quite literally an object that feels out of place in time. The concept of OOPArts has long been a battleground of interpretation. On one side, alternative historians and researchers point to such finds as hard evidence of lost civilizations, forgotten high technology, or even contact with otherworldly intelligence. They argue that mainstream science is too rigid, too invested in a linear timeline of progress to accept evidence that contradicts it. Famous examples often cited include the Antikythera mechanism, which was once considered an OOPArt before being accepted as a marvel of Hellenistic science, or the Baghdad battery, a clay jar controversially interpreted as a primitive galvanic cell. The Saqqara find now joins this provocative list. On the opposing side, mainstream academia often views the term OOPArt with deep skepticism, considering it a label that prematurely bypasses scientific scrutiny in favor of sensational conclusions. Their criticism is methodological. They argue that an artifact is only out of place relative to our current understanding, and that understanding is always incomplete. Most alleged OOParts, upon rigorous investigation, are found to be misstated, misinterpreted, or hoaxes. The mainstream position is one of extreme caution, preferring to explain anomalies through more conventional means, like ceremonial use or our own failure to grasp an ancient object's true mundane purpose, rather than invoking revolutionary revisions of history. This is precisely the debate now swirling around the Egyptian find. The team's own analysis, with its evidence of precision tool marks and mechanical wear, pulls it away from the realm of pure speculation and grounds it in tangible, testable data. This positions the artifact in a unique and powerful middle ground. It is not a vague legend or a questionable relic. It is a professionally excavated, scientifically dated object with inexplicable features. It forces the OOPArt debate to engage with high-quality evidence, challenging skeptics to provide a convincing non-mechanical explanation that accounts for all the observed details, while also challenging proponents to build a realistic model of the society that could have produced and used such devices. The artifact doesn't just ask what it is, it asks us to re-examine the very framework we use to interpret the past, testing whether our categories of possible and impossible are as firm as we believe. The artifact's enigmatic nature inevitably draws the gaze beyond conventional archaeology. In the spaces where mainstream science hesitates, alternative historical theories rush to fill the void, weaving narratives that are as captivating as they are controversial. One prominent thread suggests this technology is a relic of a lost civilization, a culture of immense sophistication that predates all known ancient empires. Proponents point to legends like Atlantis, described by Plato as an island nation with advanced engineering that sank beneath the waves in a single day. Could the Saqqara artifact be a surviving piece of such a world, a fragment of knowledge preserved by Egyptian priests who inherited it from a forgotten teacher race? This theory argues that sudden leaps in technology, like the seemingly instantaneous mastery of pyramid construction, are not the product of slow evolution but of recovering a legacy from a prior age. Another perspective posits an advanced prehistoric culture right here on Earth, one that developed complex machinery during the last ice age, only to have its achievements erased by rising sea levels and climatic shifts. The artifact, in this view, is a rare survivor from that distant epoch, somehow curated and buried by the later Egyptians who may have revered it without fully understanding its original purpose. The most speculative theories venture into the realm of ancient contact, suggesting that such precise mechanical knowledge could have come from an external, non-human source. These narratives often reference global myths of sky gods bringing gifts of wisdom to early humanity, interpreting the geared device as a kind of pedagogical tool or a discarded piece of far more advanced technology. It is crucial to separate these compelling stories from the direct archaeological evidence. The excavation report provides no tablets mentioning Atlantis, no artifacts from an unknown material culture in the same layer, and certainly no evidence of extraterrestrial visitation. What the dig site offers is a single, anomalous object in a firmly Egyptian context. Yet, the role these alternative theories play in the public imagination is undeniable and important. They speak to a deep human desire to solve mysteries, to believe that history is grander and more wondrous than our textbooks allow. They challenge the sometimes rigid boundaries of academic consensus, forcing us to ask if our current timeline is complete. While the evidence does not support these speculative claims, the fascination they generate underscores the profound impact of the find. It has become a mirror, reflecting our own hopes and questions about humanity's origins. The real power of the artifact may lie not in proving a lost civilization, but in demonstrating how a single, tangible mystery can reopen the deepest questions about our past, inviting us to wonder what other chapters of the human story might still be waiting, silent and buried, for their moment to be unearthed. The mainstream response to such a radical claim is not one of dismissal, but of disciplined caution. Leading Egyptologists, while acknowledging the artifact's strangeness, propose a series of far simpler explanations rooted in the known practices of the culture. Their most cohesive rebuttal centers on three key possibilities. First, they suggest it could be a singularly unique ritual object. Ancient Egyptian religion was deeply symbolic, and priests used specialized implements for ceremonies we no longer fully comprehend. This item, they argue, might represent a cosmic model, its gears symbolizing the eternal cycle of the sun and stars, its wear resulting from ritual anointing or repeated ceremonial handling rather than mechanical rotation. Second, it could be the product of a lone master craftsman's artistic experiment. Just as a brilliant sculptor might push the boundaries of stone carving, a gifted metalsmith, perhaps inspired by the potter's wheel, could have created this intricate piece as a demonstration of skill or a personal tribute to the concept of order, with no intention of it being part of a working machine. The final and perhaps most pointed argument is that we are misinterpreting natural processes. The precise-looking wear on the gear teeth, they caution, could be the result of selective corrosion over millennia, where certain crystalline structures in the metal wore away more evenly, creating the illusion of mechanical polishing. The straight channels might be casting flaws or later damage from tomb collapse, not deliberately machined guides. This is where the philosophical tool known as Occam's razor enters the debate. The principle suggests that among competing hypotheses, the one with the fewest assumptions is often preferable. The mainstream view applies this razor neatly. Their explanation requires only known elements, a creative artisan, known metallurgy, and symbolic religious practice. It makes no assumptions about lost workshops, widespread unknown technologies, or complex machines absent from the record. It is, on the surface, the simpler path, but proponents of the machine theory counter that Occam's razor is being misapplied. A hypothesis must account for all the evidence, not just the convenient parts. The simpler explanation, they argue, is not the one that ignores the most data. To dismiss the uniform, directional wear patterns as random corrosion requires assuming a highly improbable natural coincidence. To see the perfect symmetry and identical gear teeth as a mere artistic experiment ignores the clear logic of their design for interaction. The machine hypothesis, while introducing a new assumption about technological capability, actually provides a more straightforward, functional reason for every observed detail: the shape, the materials, the wear, and the assembly. It argues that the simplest explanation for an object that looks engineered, wears like a machine, and is assembled like a mechanism is that it was, in fact, a machine. The real complexity may lie in forcing a ceremonial or artistic interpretation onto a form that so elegantly solves a mechanical problem. This stalemate between simplicity of elements and simplicity of explanation is the core of the intellectual stalemate, a clash not of evidence, but of the very frameworks we use to interpret our ancestors' minds. The debate between interpretation and artifact seemed at an impasse until modern technology offered a way to see the unseen. To move beyond surface speculation, researchers employed a suite of non-invasive scanning techniques, essentially giving the object a digital autopsy without ever touching a brush to its ancient surface. The first and most revealing of these was a high-resolution computed tomography scan, the same technology used in hospitals to create three-dimensional images of the human body. For the artifact, this was a revelation. The CT scan sliced through the corroded metal shell, mapping its internal structure with incredible clarity. It confirmed the hollow nature of the housing, but more importantly, it revealed something invisible from the outside: internal threading. Within the square drive socket, the scan detected the faint, spiraling pattern of a screw thread. This was not a smooth hole, but a threaded socket designed to receive a matching threaded axial for a secure, adjustable connection. This single detail shifted the engineering assessment dramatically. A threaded connection allows for precise axial adjustment, for fine-tuning the position of a component along the shaft. It is a hallmark of advanced mechanical design, aimed at calibration and control, far beyond the needs of a static ceremonial object. Complementing this, a structured light three-dimensional laser scanner was used to create a perfect digital twin of the artifact's exterior. This process projects a grid of light onto the object and uses cameras to measure the minute distortions in the grid caused by the surface contours. The result is a point cloud model accurate to within a fraction of a millimeter. This model allowed engineers to perform virtual measurements and tests that would be impossible on the fragile original. They could calculate the exact pressure angles of the gear teeth, confirming they were cut to efficiently transfer rotational force with minimal slippage. They could analyze the depth and parallelism of the three radiating channels, proving they were not casting flaws but deliberately machined features with consistent dimensions. The scanner also revealed subtle tool marks on the channel floors, a series of fine, parallel striations that curved ever so slightly, the telltale signature of a cutting tool that moved in a controlled arc, further evidence of a guided manufacturing process. Finally, photogrammetry, the science of making measurements from photographs, was used to document the artifact's relationship to every other object in the tomb. Hundreds of overlapping high-resolution images were taken from every angle, then stitched together by software to create an immersive, measurable three-dimensional model of the entire find site. This digital reconstruction allowed archaeologists to revisit the context endlessly, examining the artifact's exact position, its orientation, and its proximity to other items. It solidified the stratigraphic evidence, visually proving the object lay in an undisturbed layer, and helped rule out any possibility it was a later intrusive deposit. This technological triad, the CT scan, the laser model, and the photogrammetric map, did not just provide more data, it provided a new language of evidence. The internal thread, the precise pressure angles, the machined striations, these are not poetic symbols, they are the unambiguous vocabulary of engineering. The scans transformed the artifact from a curious relic into a detailed set of blueprints, a data set that speaks directly to the intent of its makers. In a profound twist, our most advanced 21st century technology became the essential key for decoding the sophisticated mind of a 4,000-year-old craftsman, revealing a level of deliberate technical thought that quietly redefines the horizon of ancient innovation. But a blueprint is not a machine. To understand what this object could truly do, researchers knew they had to move from digital models into the physical world. A call went out to a unique community of experts, including precision machinists, historical engineers, and even skilled model makers who specialize in recreating ancient technology. Their mission was to use the exact scan data to build working replicas to see if the silent artifact could be made to speak through motion. The first and most critical step was to determine the most basic question of all: could it even function as a gear? Using three-dimensional printing technology, they created a perfect plastic copy of the central geared ring. They then crafted a simple pinion gear, a smaller toothed wheel, based on the wear patterns and the standard mechanical ratios of the era. When they meshed the two, something remarkable happened. The gears engaged smoothly. The 24 teeth, designed over 4,000 years ago, transferred motion perfectly to the smaller gear without jamming or slipping. This simple test was a profound moment. It proved the artifact was not just shaped like a gear, it worked as one. The precision was not an accident, it was intentional and effective. With this confirmation, teams began constructing full-scale models of the entire assembly. One group, focusing on the idea of an astronomical tracker, built a model where the central gear was turned by a simple hand crank on the square axle. This gear then drove a series of smaller gears on a plate mounted on those 3 ceramic bearing pins. They marked the plate with symbols for constellations. As the crank turned, the plate rotated at a different, slower speed, demonstrating how the device could have tracked the changing night sky over weeks or months. The model worked, but it revealed a challenge. The system required precise alignment and very low friction to operate smoothly, something the original craftsmen would have had to master. Another team, pursuing the surveying instrument theory, created a different configuration. They fixed the artifact's housing to a wooden base and inserted a long, threaded sighting rod into the square socket. By turning the central gear, they could make the sighting rod tilt up and down with minute-controlled adjustments locked in place by the gear teeth. This created a stable and adjustable aiming device, ideal for aligning distant markers across a desert plateau. However, this model highlighted a different issue. Without a locking brake or a worm gear, the mechanism could slip if jostled, suggesting a missing component for securing the setting. Each reconstruction, whether digital or physical, taught a new lesson. Some configurations, like a simple water pump mechanism, locked up immediately. The geometry was wrong. Others, like a device for dispensing a measured amount of liquid or grain, operated flawlessly, the channels acting as guides for a sliding gate. The most successful models shared common traits. They used the gear for precise counting or positioning. They utilized the bearing pins for a stable moving plane, and they interpreted the square socket as an input for controlled human power. These reconstructions did not prove a single purpose, but they proved viability. They demonstrated that the artifact's design is inherently functional, capable of enabling complex tasks from timekeeping to measurement. The failures were just as instructive, ruling out whole categories of use and sharpening the focus on what the geometry inherently allows. This hands-on testing moved the debate from abstract speculation into the tangible realm of physics and mechanics, where an idea must either move or seize up. In doing so, it gave silent, corroded metal a voice, whispering across millennia that its makers understood the poetry of motion, captured in bronze and careful calculation. This single, intricate mechanism inevitably casts a long shadow over the greatest architectural achievements of its era. The pyramids of Giza, the towering obelisks, the vast temple complexes, all stand as monuments to a scale of precision that has baffled observers for centuries. How did a civilization with copper tools and stone hammers achieve such near-perfect alignments, such seamlessly joined multi-ton blocks, such level foundations across acres of desert? The discovery of a geared device suggests a new and compelling possibility, that the Egyptians may have possessed a hidden layer of technical instruments, now almost entirely lost, which guided their hands. Consider the foundational challenge of aligning a pyramid's base to the cardinal directions, north, south, east, and west. The Great Pyramid of Khufu is aligned with an error of less than 1/15 of a degree. Achieving this across a base length of over 750 feet using only simple sighting poles and the stars seems almost superhuman. But what if the priests and architects had a more sophisticated tool? The artifact's design, with its stable base plate and central geared ring, is strikingly similar to the core of a simple theodolite, a surveying instrument for measuring horizontal and vertical angles. A replica model demonstrated that by mounting a sighting alidade, a straight-edge viewer, onto the square drive axle, the geared mechanism allowed for incredibly fine, incremental adjustments in aim. Turning the central gear, one tooth could shift the sightline by a precise fraction of a degree, enabling surveyors to lock onto a star's transit with unprecedented accuracy and then transfer that angle directly to the construction site. This would transform the task from an art of estimation into a repeatable mechanical process. The precision stone cutting presents another profound puzzle. The granite and limestone blocks of the pyramids and temples fit together with joints so tight that a razor blade cannot slide between them. The common explanation involves pounding with stone hammers and grinding with sand slurry, a brutally laborious method. Yet, the evidence of rotary cutting tools on the metal artifact opens a different line of inquiry. If they could use a mechanical aid to cut precise channels and gear teeth in copper alloy, could a scaled-up version of that technology have been used to dress stone? A large, bow-driven lathe or a rotary saw, perhaps using a copper blade fed with abrasive sand, could explain the flat, smooth surfaces and consistent angles found on casing stones. The artifact does not prove they had such machines, but it proves they understood the principle of guided, rotary cutting motion, a conceptual leap that could have been applied to materials far larger than a small metal box. Finally, there is the Herculean task of transportation and placement. Moving a 200-ton granite obelisk from a quarry and erecting it upright is a feat of logistics that strains belief. While ramps and sledges are the accepted theory, the control required to lower such a monolith into a precise foundation trench without shattering it is immense. A geared mechanism, perhaps acting as a primitive but powerful brake or winch, could have provided that control. Imagine a large wooden capstan, its axle fitted with a series of these bronze gear components, creating a compound pulley system that allowed teams of workers to lower a colossal weight in slow, manageable increments, with the gears preventing a runaway descent. The wear on the artifact's teeth speaks of sustained, loaded use, exactly the kind of strain such a heavy lifting apparatus would endure. The connection here is not that the small artifact itself was used to move blocks, but that it represents a class of technology, a philosophy of mechanical advantage and controlled motion that could have been scaled to meet the monumental challenges of the age. This perspective does not diminish the achievement of the Egyptian workers, it enhances it. It suggests their genius was not only in mobilizing vast human labor, but in complementing that muscle with delicate, ingenious minds that could harness physics through clever devices. The silent gear from Saqqara may be a tiny key to a very large door, hinting that the pyramids were built not just with brute force, but with brilliant, forgotten mechanics. This single object forces us to reconsider the entire story of human ingenuity. For generations, the history of technology has been taught as a linear march, a steady progression from simple tools to complex machines, with each civilization building directly on the discoveries of those before it. We see the potter's wheel in Mesopotamia, the aqueduct in Rome, the printing press in Germany, and the steam engine in Britain, a neat sequence of cause and effect. The confirmed existence of a sophisticated geared mechanism in Old Kingdom Egypt would shatter that tidy timeline. It would reveal a startling possibility that the spark of complex mechanical thought was ignited not once in one place and in one continuous line, but multiple times in different cultures, only to be lost and later rediscovered. This artifact suggests an earlier, independent flowering of engineering philosophy, a branch of innovation that grew in the shadow of the pyramids, then seemingly vanished from the record for thousands of years before similar ideas re-emerged in the Hellenistic world with devices like the Antikythera mechanism. This is not about claiming the Egyptians invented everything, but about recognizing that the capacity for such invention is a fundamental human trait that can manifest under the right conditions, and that those conditions may have existed far earlier and in more places than our textbooks allow. It challenges the very notion of technological primacy, the idea that one culture holds the patent on progress. Instead, it paints a picture of a more dynamic, fragmented, and mysterious past where brilliant ideas could rise, be applied to the needs of a specific society, and then fade from common knowledge, preserved only in fragments or forgotten entirely until the wheel of discovery turned again. The implications ripple outward. If such a device existed in Egypt, what other pockets of advanced technical knowledge might have flourished and dissolved in ancient India, China, or the Americas, leaving behind only whispers in myth or enigmatic artifacts we have yet to correctly interpret? This perspective transforms history from a single, well-lit path into a vast, dimly lit landscape, where beams of advanced understanding occasionally flash in one region, only to leave the rest in darkness until the next flash illuminates another. It suggests that human progress is not a straight line, but a story of fits and starts, of brilliant leaps and profound forgetfulness, where the most important chapters may be the ones we are only just beginning to read. Today, the artifact resides in a secure, climate-controlled storage facility attached to the Egyptian Museum in Cairo. It is not on public display, a decision that reflects its contested and unresolved status. Officially, it is catalogued as an unusual metallic object, 5th dynasty, function unknown, a deliberately neutral description that reveals nothing of the fierce debate surrounding it. Within professional circles, the discussion has reached a fascinating stalemate. The initial excavation team published their findings in a respected archaeological journal, detailing the context, the dating, and a preliminary description of the object. However, their paper carefully avoided the term machine, opting instead for phrases like complex fabricated object and item of probable ritual significance with atypical mechanical features. This cautious language is the key to understanding the academic impasse. No major, peer-reviewed study has yet been published that explicitly argues for the artifact as a component of a purposeful ancient machine. The evidence, from the wear patterns to the internal threading revealed by scans, is discussed at specialized conferences and within the pages of journals focused on archaeometallurgy or the history of technology, but always framed as an anomaly awaiting explanation, not as proof of a paradigm shift. The conversation is vibrant yet fragmented, occurring in hallway conversations at symposiums, in detailed blog posts by independent researchers, and in the appendices of reports focused on broader Old Kingdom material culture. The machine theory, while compelling to a growing number of engineers and forward-thinking archaeologists, remains in a kind of academic limbo. It is treated not as a settled fact, but as the most provocative hypothesis in need of the most rigorous proof. Mainstream Egyptological institutions, guardians of a deeply conservative and evidence-driven field, are waiting for a smoking gun, a second such object found in an equally clear context, or a definitive textual reference that can break the silence of the artifact itself. Until then, the official stance is one of intrigued skepticism. The artifact is studied, its scans analyzed, its composition probed, but it has not yet rewritten the textbooks. This stalemate is not a sign of failure, but of science working as it should, moving slowly and demanding overwhelming evidence before redrawing the map of history. The mystery persists precisely because the artifact is too well documented to dismiss, yet too singular to easily accept. It sits in its quiet vault, a silent question mark cast in bronze, waiting for the next piece of the puzzle to emerge from the sands. While scholars debate in measured tones, the discovery ignited a firestorm in the world beyond the laboratory. Headlines blared with irresistible certainty, proclaiming an ancient Egyptian computer found or a lost high-tech device that rewrites history. Documentary specials, often featuring dramatic reenactments and stirring music, framed the artifact as a definitive key to unlocking secrets the academic establishment was supposedly ignoring. Online, the reaction was a tidal wave of speculation. Forums dedicated to alternative history and ancient mysteries lit up with thousands of posts analyzing every grainy photograph, proposing elaborate theories about its connection to Atlantis or extraterrestrial visitors, and passionately arguing over its implications. This public narrative, fueled by a natural hunger for wonder, created a powerful, simplified story, a tale of a single object that solved a grand mystery. Yet this very excitement often widened the chasm between public perception and the painstaking reality of archaeological science. The measured, tentative language of the official report, with its unusual metallic object and function unknown, seemed almost deliberately dull in comparison, a cautious whisper drowned out by a roar of certainty. This gap is not merely about information, it is about two very different ways of engaging with the past. The public narrative thrives on revelation and resolution, the satisfying click of a puzzle piece falling into place. Science, however, operates in the realm of probability, peer review, and incremental understanding, where a single click is rare and a new piece often makes the puzzle larger and more complex. This divergence fuels a fascinating cycle. The sensational headlines generate massive public interest, which in turn funds more research and brings new eyes to the field. But that same sensationalism can breed deep skepticism toward mainstream experts, who are sometimes portrayed as gatekeepers hiding the truth. The result is a paradox. The very media storm that makes the artifact famous can also make it harder for the nuanced, evidence-based story to be heard. The artifact thus exists in two parallel worlds, one of gripping television specials and online deep dives, and another of quiet museum storage and academic conferences, each telling a very different version of its silent story. Yet this profound mystery is now guarded by a set of equally complex modern challenges. The artifact's very fragility dictates a cautious, almost reverent approach to its study. Preservationists face a delicate balancing act: how to unlock its secrets without causing it to fade into dust. Every time it is handled, even with gloved hands and under controlled conditions, microscopic particles of the ancient metal can flake away, erasing potentially vital clues etched into its surface. More aggressive testing, such as taking a physical sample for metallurgical analysis, could yield definitive data about its alloy composition and manufacturing techniques, but it would also mean destroying a small piece of an utterly unique object. This creates an ethical dilemma as intricate as the gear teeth themselves. Is the knowledge gained worth the permanent loss? The debate among curators and scientists is deeply polarized, with some arguing that non-destructive scanning has provided all the data we can safely gather, while others contend that a tiny, carefully chosen sample could answer the core question of its origin and purpose once and for all. This tension between preservation and knowledge is the quiet battle fought in museum basements around the world, where the legacy of the past must be weighed against the understanding of the future. Beyond the physical preservation lies the question of cultural patrimony. The artifact was unearthed on Egyptian soil, and by international convention and law, it belongs to Egypt and its people. This rightful ownership brings immense responsibility and legitimate control over who gets to study it. The Egyptian Ministry of Antiquities must navigate requests from international research teams, each with their own specialized equipment and theories. Granting access is necessary for advancing global understanding, but it also risks the object traveling or being subjected to methodologies that its home institution may not fully endorse. There is a growing and vital conversation about ensuring that Egyptian scholars and engineers are at the forefront of this research, interpreting their own heritage through a lens that respects both cultural context and scientific rigor. The goal is to avoid a colonial dynamic where a precious find is extracted, studied abroad, and its narrative defined by voices far from its origin. True understanding of this object may depend as much on inclusive collaboration as on the precision of a scanning electron microscope. For independent researchers and the public, access remains another layer of challenge. High-resolution scans and models have been partially shared, allowing for global digital analysis and the fascinating replica projects we discussed earlier. However, the full data sets, the raw CT scan files, and the complete photogrammetric models are often held closely by the primary institutions involved. This is partly for security and to protect the integrity of ongoing study, but it also limits the crowdsourcing potential of the global scientific community. Could an engineer in Germany or a horologist in Japan see a detail in the data that everyone else missed? The ethical path forward seems to be a gradual, managed release of information, one that protects the artifact's physical safety and the dignity of its cultural home, while slowly inviting the world to contribute to solving its puzzle. The artifact, then, is not just a relic of ancient technology, but a test case for modern ethics, a mirror reflecting how we choose to steward the most disruptive pieces of our shared human story. The artifact's silence leaves us with a constellation of unanswered questions, each one a path leading deeper into the mystery. First and most obvious, what was its exact purpose? Was it an astronomer's calculator, a surveyor's guide, a priest's sacred apparatus, or something entirely beyond our current categories of thought? Without a manual or a clear depiction of its use, its function remains a compelling puzzle. Closely tied to this is the question of operation. How was it powered and controlled? We see the square socket for an axial, but was it turned by a hand crank, a falling weight, or even a slow trickle of water? The mechanism we have is likely just the heart of a larger device, and the nature of that complete apparatus is lost to us. Then there are the human questions: who made this and for whom? Was it crafted in a royal workshop under the direct order of a pharaoh, or was it the product of a lone, brilliant artisan in a provincial town? The fact it was found in a non-royal tomb suggests its owner, perhaps a high-ranking official or a temple astronomer, valued it enough for the afterlife, hinting at its immense practical or spiritual worth. Perhaps the most tantalizing question of all is one of scale. Is this object unique, or is it a single survivor from a series? Did the Egyptians produce more of these devices, and if so, where are they? This leads directly to a profound possibility. Could similar pieces be sitting unrecognized in museum basements around the world, catalogued simply as ritual bronze objects or unidentified fittings, their true mechanical nature overlooked because no one was looking for gears in Old Kingdom Egypt? Future research now has a clear and urgent roadmap. One priority is to subject the artifact to even higher resolution imaging, perhaps using synchrotron radiation or advanced electron microscopy, to map the microtopography of its surface in ultimate detail. This could reveal the subtlest tool marks, identifying the exact type of cutting point used and even the direction and speed of its strokes, effectively giving us a fingerprint of the ancient workshop technique. Another avenue is a renewed, targeted search through the textual record. Egyptologists, now armed with the physical parameters of the object, can re-examine inscriptions and papyri with new eyes, looking for descriptions of instruments, devices, or vessels of turning that might have been previously mistranslated or misunderstood. A broader, systematic review of museum collections is also proposed, using three-dimensional scanning on unidentified bronze artifacts from the same period to search for similar geometric patterns, wear, or evidence of assembly. Each of these paths offers a chance to move from a singular anomaly toward a pattern, and a pattern is the beginning of understanding. The artifact is no longer just an object to be explained. It is a question that has begun to systematically interrogate our entire framework of the past, demanding new methods and new ways of seeing. The search for answers has only just begun. Ultimately, this artifact embodies a profound and unresolved tension. On one hand, its physical form speaks a clear, logical language of engineering, precision gears, deliberate wear patterns, and internal threading that together whisper of function and motion. On the other, it stands in absolute silence within the historical record, a solitary echo with no clear origin story, no workshop diagrams, and no companion pieces to confirm its place in daily life. This is the core of the mystery, a clash between what the object demonstrably is and what our established narrative says could have existed at that time. Whether one sees a ritual object of unparalleled complexity or the heart of a forgotten machine, the conclusion is inescapable. This find demands we re-examine the ceiling of ancient Egyptian technological capability. It suggests that our map of the past, drawn from surviving art and texts, may have missing continents, entire realms of practical knowledge that were so specialized or perhaps so commonplace, they never made it into the tombs of kings or the hymns to gods. This is how understanding evolves, not through the steady accumulation of confirming facts, but through the disruptive power of a single, stubborn anomaly that refuses to fit. The artifact from Saqqara is a gift of profound curiosity, a reminder that history is not a closed book but a living puzzle with pieces still waiting in the earth. It invites us to look at the familiar landscapes of the past with new eyes, to question the boundaries of what we think we know, and to remain forever curious about the quiet secrets still buried, patiently awaiting their moment to turn the page.